You're good to go.
Okay, let's begin. Okay, so hello everyone. My name is Lev Veda. I'm a senior software engineer at Red Hat, and for about the last 10 years, I'm working on Rev/oVirt. So a little introduction: what is Rev, oVirt, etc. So Rev is Red Hat Enterprise Virtualization product. It allows to manage all sort of virtualization workloads. And oVirt is our upstream community project, which basically it's something similar to what's Fedora to RHEL, but in our case, it's a lot more closely related to Rev. So the source code is very, very similar. And what is OCP? I think most people in Red Hat know is the OpenShift container platform. So where it all began with our oVirt TinyCore Linux project. It all began with the OCP on Rev initiative, but we have also as part of our integration team of Rev, and it basically allows to run OpenShift on top of Rev. And when we began working on it, it basically required to writing a lot of additional code to communicate between the OpenShift and Rev through the API that Rev provides. And of course, when you write a new code, you need to add some tests. So Janos, our team member that was working on it, began to write some additional tests for this SDK. And he got a need. Basically, he needed to test that the code works. And since it also was designed for people to run on upstream, he needed to create some small VM, really, really small one, that somebody can run to make sure that the code performs as intended. And he didn't want it to use anything like a regular operating system because it was simply too large. And he basically had only one requirement in the beginning, to have a VM that just starts, shows some message to basically show us that the operation succeeded, VM started, it operates, all good. So what he actually created was a very, very small VM of just one sector, basically based on MBR. So it just does just that. It, of course, was written in pure assembly. And initially just printed the message and quit. That's all that he did. And later it was actually improved with the contribution from other people. So now it shows some cool ASCII code, ASCII art on the screen. And also I added support for serial port communication. So the message could be sent out through the serial port. And then the test could be made in automatic way. So we could test that it actually runs also in automatic way. Okay, so how it looks like. This is what it looks. You see, very thin. Just a simple message. All cool and well. But as we actually continued to work on this initiative, a new requirements arose in the OCP on Rev. Because we needed to test more functionality of the library. And the first one was a requirement basically to shut down this VM externally. And then it appeared that it's more complicated than we thought because that requires implementing ACPI, which of course in such small code base, it was problematic. We actually searched other similar projects. I searched FreeDOS, for example, to see if they get this already implemented code for ACPI, and we could not find anything. And then we met a second roadblock, which was even more problematic for us because it was a real blocker. Because for testing, we required to get information from inside the VM. And it basically required us to communicate with a QEMU guest agent. And that was like a real problem, because in order to communicate with it, we needed actually to get all the infra into this VM. And it required basically to implement Virtual serial driver. And for it to work, it actually required to implement PCI device handling, and of course, create the QEMU guest agent, or at least mock something which simulates it. And we checked this, we made our investigations around it to check what our options are. And it proved that it simply doesn't worth the time invested, because it's still feasible. We could create something simple in assembly. Of course, it will not fit into one sector. So the project from a 512 byte VM would transition to something like a few 100 kilobytes of VM, but still it would require a lot of time, which was better spent somewhere else. So after checking all other options, it seems that that project was basically dead for its purpose. So it's still some cool project. If you still need some VM for testing the functionality of hypervisor, it's still something really nice. But for our options, it was simply could not work any longer. So the next option, of course, was to use some small Linux distro. And the question that normally arises when we speak about this project is, well, why not simply to use something like general distros, even our own, like RHEL or CentOS? And the short answer is that it basically is just too large. So any image, when you install the current version of RHEL or CentOS, the minimal requirements that our documentation says it's over 3 gigabytes of disk space. And we actually worked on the RHEL and CentOS, and we tried to minimize the size of the installation to cut out the pieces that we don't generally need. And still, the installed image was well over 1 gigabyte in size, which was simply unacceptable for our specific purpose, because we wanted this to be available for people to actually pull on the tests. And asking for people that want to participate in the project to pull 1 gigabytes or more data was simply not acceptable. So we had to move to some other options, of course, and we began checking other small Linux distros. And between those, we chose this one, the Tiny Core Linux.
Pardon me, can I ask a question?
Yes, of course.
On your previous slide, you mentioned that it was too big in size. Is this even the case if you use like a UBI style reduction that they do for RHEL?
Yeah, well, the issue was that we wanted to allow the community to participate. And that means that somebody pulls the basically the project to his computer and runs its own environment. And in this case, we can't use like for our internal tests, for example, we have a framework for Rev, for example, which is called OST, which uses internal infra. And then the images get pre-installed in. You can simply pull them once and work inside that environment. But in this case, it was intended for upstream community. And because of that, we wanted it to be minimal in size. Also, we began to transition into the GitHub repositories, which again, something upstream. And the size of the VM is, in this case, is actually important. It's not something you pull once and reuse. And for the upstream user or contributor, anyone that wants to contribute, it's still, even if you pull it once, if you need to pull like 1, 2, 3, and more gigabytes in size just to get this test image. For the VM, it's still quite large. So we wanted to get something much smaller. Does this answer your question?
Yes, thank you very much.
Okay, thanks. Okay, so between the actually a number of different small Linux distros, but looking around them, we choose this one. First of all, because it's one of the smallest, it's just around 20 megabytes in size, which is, well, it's still a lot larger than 512 bytes, of course, but it's like 100 times and more smaller than a typical CentOS installation. So it was quite good. On top of that, it uses a quite recent kernel, which is also good for us because there are smaller distributions, but they use quite old kernels. So they potentially could miss the features that we need in the future. It's not feature-proof. And what is also quite important for us, it's maintained. So the tiny core, they have a community around it. They regularly release new releases. They build new versions. So it's not that project like there's some projects that haven't released anything for a few years, which simply means that we base something on a dead project. So it's proved to be something good. So basically what's in Tiny Core Linux, I try to get the technical details out as much as possible because I said that the talk will be basically an introduction level. So just like small details. So it's quite simple distro. It basically consists of a bootloader, a Linux kernel, and initramfs image, which inside of it, it's most of it, it's BusyBox, which is a toolkit for utilities, and some scripts that glue it all together. So it also was, on the first side, it was quite good for us because it's simple. It means it's simple to modify for our needs. But as we began to work on it, we also see that it's what's called, it's not all honey. Because first of all, the Tiny Core project, they don't provide infra. They basically provide you with the release and they give you some instructions on building it. If you want to build your own custom version of Tiny Core Linux, you need to get the instruction and build it manually yourself. And because of the way that it's built, it requires manual modification for almost all cases because it's almost stateless. It sits inside, you get initramfs image. So if you want to modify anything in the system, even if it's installed, because they support both the ISO, which you can load, and of course it's stateless, and you can do the installation. But the installation also installs it mostly as is. It uses the same initramfs image. So everything which you want to modify, if you want to modify some script or add anything, then you need to do this modification and rebuild the image and basically rebuild the ISO. So your modification will actually be applied to it. Okay, so it's also means that it's not a simple modification as you do with the regular Linux distribution where it's basically stateful. You can install the image and then do some modification and it will be saved, right, on the block device. Here, for any modification that you want, you need to basically create a new initramfs image to include these changes. And it proved that, of course, we knew that we will need to do this modification. So it was obvious. And also the kernel, in our case, it had to be rebuilt because for some of the options that we wanted, we wanted a support for hot pluggable memory in the kernel, and the plain TinyCore Linux kernel, they have this option simply disabled by default. And of course, we need also to rebuild some of the tools and packages, which in order to make the distribution work the way that we wanted, due to the process that it requires, we also had to rebuild our own. So what we did so far for this project, we created an automatic build and CI process in GitHub. So in our case, we have environment which, unlike TinyCore Linux, which all manual, we can make modifications, push this modification to GitHub and work like in the way that most people expect. So you push your modification, if you merge it, you basically get a rebuild automatically. So you have a full CI there. And inside the code, what we did, we added QEMU guest agent, which was one of the requirements, initial ones. So our image, unlike the plain TinyCore, you get this already included. By default, it's included and it's running. So when you start our ISO image inside VM, it's already running. It's able to communicate in case of if it's running inside of, let's say, Rev or oVirt, it supplies the information into the manager. We added and enabled ACPI support. So now you are able to request the shutdown of the VM externally. Before that, if you run just a plain TinyCore inside Rev, for example, you can't request it to be shut down. You can only request to power it off. So you firstly can kill the VM, but you can't say externally to the VM, please shut down, unless you go into the terminal and make the power off. So in our case, it's supported. We added the support for hot plugging of CPU, memory, and network adapters. So our distro is able to basically work with it out of the box. You can add CPU and it becomes online automatically. You can add memory. This was actually the most tricky one, because it both required the kernel recompilation and some modification in the parameters. And you can add the network adapters and they become online also automatically. We enabled support of IPv6. So now something else, which is you can add this feature in TinyCore as well, but it won't be persistent in their case, because the way that it works is that you can load TinyCore, you can add the extension, and it will work until the reboot. In our case, it's enabled in the plain both ISO and the image. And we added IP tools, because by default, you have only the ifconfig command. And we added the support in BusyBox for IP tools. So you have the IP family of the commands. And currently, it's all in approximately 32 megabyte ISO image and 22 megabytes in QCOW image. Okay, this is some demo how it looks like. So as you can see, you get IPv6 addresses out of the box. Okay, this is an example of a network adapter hot plug.
Hey, Lev, this is your 10-minute warning.
Sorry?
10-minute warning.
Okay, great, thanks. So let me try to speed it up. So in this case, as you can see, we added a new adapter online and it became visible. This is an example of the RAM hot plug unplug functionality. So we have both actually supported. As you can see, initially it has approximately half gigabytes of RAM. Then I add this online, add this memory without VM to be shut down. And then I again do the opposite operation of unplugging the memory. And it again gets only half gigabytes of RAM. And this is the case of CPU hot plug. So as you can see, initially we see only one CPU, and then I add another CPU, and we can see that we have two CPUs. Okay, so what we are currently working on, we are basically working on adding DHCP v6 support for IPv6. Actually, in the current release, it works with the ISC DHCP server, and we're still trying to understand why it's not working for DNS mask server 1. Okay, so I almost over. This is the references for the projects. The first one that we talk about, the 512-byte VM one. The second is the one that we talk about, the oVirt Tiny Core Linux. This is the project. By the way, you can clone the repo, fork the repo in your own GitHub account, make modifications, and it will be rebuilt because we are using built-in GitHub runners. So you can easily play with the project and modify it. And the last one is the link for the base Tiny Core Linux. Okay, sorry, this one is irrelevant. So any questions?
This was great. Thank you.
Okay, thank you very much.
Thanks. Great summary, Lev.
Thank you.
Okay, thanks. Any other questions? Any?
Yes, I have a question. So you had a slide where you listed the final size of the image. Do you keep an
Yes.
inventory of what contributes to the 32 megabytes, and what in the future to see how that grows or if it stays stable?
Yeah, of course. I didn't want to get into the technical details into the process of implementing features. Specifically for the RAM hot plug functionality, it's only available in the 64-bit Linux kernels. So initially we began to work with the 32-bit version of the Tiny Core. And it's smaller. Basically, the difference is some of it's support for UEFI in ISO. So it adds some additional extra space. And currently, I haven't mentioned UEFI because it's currently only supported in ISO, not in QCOW image, because the installer doesn't support it for now.
Gotcha. Thank you.
Okay, thanks. Any other questions?
Yeah, sorry if I missed it at the beginning, but do you use this in any typically very small hardware environments?
No, yeah, it can be used like Tiny Core. It's built for like some older hardware, and with the minimum requirements, because its requirements are very, very low, of course. But in our case, we only used it for our testing environment, so it was specifically tested and run on virtual machines. That was our purpose.
Thanks.
Okay, thank you. Any other questions? Okay, I think that means all. Thank you very much.
You.
All right, thank you. I'm going to stop the recording, and I guess we'll just take a break until 8:45.
Okay, sounds great. Thank you.